Now there are two other functionals over lists that are also very important and are used regularly. And one interesting thing about them is that they're closely related to map. Those are fold left and fold right. And first let's look at fold left. And fold left, and in fact also fold right, are functionals that are found in the standard prelude of Haskell. Fold left, which we'll describe first, takes a binary function, inchoate form, an accumulator, and a list, and produces a value. So if our binary function is plus, takes an x and a y and adds x to y, then we would expect that if we use foldl with the plus function and the initial value 0 and the list 1, 2, 3, 4, we would add 1, 2, 3, and 4, and that would give us 10. So let's see how we can implement this in Haskell as foldl prime. Foldl prime is a function that take a function f and an initial value a and some list, and then apply f successively to the elements of the list. If there are no elements in the list, we just return the initial value. If fold left prime is applied to f and the initial value x, a and a non-empty list of x and some further x's, what do we get? Well, the idea is that first we apply f to a and the first element of the list, and then we take this and we fold with f, and the initial value is now this, and the list for which this is the initial value is the tail xs. So let's take that as our implementation of foldl prime, send this to Haskell. So what happens if we take foldl prime and apply it to the plus function? We can write the plus function in this way by taking the plus symbol and putting it in parentheses and using 0 as the initial value, and then 1, 2, 3, 4. What do we get? Well, we got 10. And that's what we would expect. But what is the type of foldl prime? Let's figure that out now. Now, what is the type of foldl prime? Now, fold left prime is a higher order function. Its first argument is a function f, and f is a function that takes two arguments. We see that here f is applied to an a and an x. So this function must have type t1 to t to some t2 here. And then we also see that the next argument to which fold L prime is applied is the initial value, and the type of the initial value must then be t1. So it's t1 here, and next the argument we get is a list, and it's a list of elements of type t. Because this is a list of second arguments, we see that we're applying the second argument from the list one at a time. So this is t list. And what do we get? Well, we get something that's of the type of A, we can see that, and the type of A is t1, so this should be t1. Now there's a further simplification we can make, because if we look at this, this is the return type of f, and we can see that the return type of f is it's actually just t1. So here we should write t1. So that's the type of foldl prime according to what we figured out. Let's see what Haskell says about this. Type of foldl prime, what do we get? We get what we figured out, so that's very nice. And as before, in our analysis of the type, we did not say anything about T1 or T, so this is again a polymorphic type. So that's what we get here. Now, what is the type of foldr prime? Well, let's see. Foldr prime takes 3 arguments. The first argument, which we here call f, is a function of type t to t1 to t2. We'll figure out what t1 and t2 are in a moment. And then the next argument takes is something, the initial value of type t3. And then we take an argument of list type, and to figure out what the list type is, and we'll figure that out in a moment, t4, we'll need to look at what the result type is also. What is the result type? It's some t5. But what is t5 first? Let's see. We can see from the first clause, we can see here that the result type of foldr is a type of A, so that's type of T1. So this is really T1. So that's the first thing we notice. Now, what about the type here? What kind of type do we have here? What's the type T4? Well, it's clear from this that X has type T4, and we see that F takes 2 arguments, and the first one is X, so this is really just T. Now what about T3 then? Well, let's see here. This is the type of the initial value A, but that's also what appears here, and A has type T1, so this T3 is just T1. So this is T1. Now what about T2 then? Well, we can see from what we have here that F takes 2 arguments. The first one has type T, second one has type T1, and the result of applying F to these 2 arguments is something of type, the return type of foldr, and we know that's T1, so this T1 is just T1. So that's the type of fold R prime. Let's see what Haskell would like to say about that. There is another folding functional, which is foldRight, and foldRight is also in the prelude, so here we'll define a foldRight prime, which does what the foldRight in the prelude does. Fold left was so called because it folds F around the values of the list from left to right. We first use F with the initial value and the first element of the list, and we use that as the new initial value, and then we fold along the tail. But we might as well do things in the reverse order, and that's what fold right does. Fold right prime, fold right when applied to a function and an initial value f and an empty list just gives us the initial value. There's no difference there. Difference happens when we look at the other clause, which is that of what happens if we apply fold right prime to f, the initial value and a non-empty list of x and some x's. Here the idea is that we now apply fold right prime to f at the initial value and the tail. We get some value out of that, and then we apply that to, we apply f to that, f and x, the head, and that. So that's fold right. Let's see what happens if we give this to Haskell. Everything is fine, Haskell says. What happens if we now apply fold right to the addition function, to the initial value 0 and 1, 2, 3, 4? Gives 10 again. So what's the point? You might ask, what's the point? Fold right and fold left are the same thing. Well, not really. Fold right and fold left agree. If the function f that we're folding with is associative and commutative, some functions are neither associative nor commutative. An example is subtraction. Let's see what happens if we fold left with respect to minus and the same initial value in 1, 2, 3, 4. Now we get minus 10. Now instead let's fold right. What do we get? Now we get minus 2. So fold left and fold right only agree if the function in question that we're folding, which is f, is associative and commutative. So fold left and fold right are not the same thing. Now the burning question is, of course, what's the type of fold right?
If f is a commutative and associative function, folding it with fold left and fold right and a given accumulation initial value will always yield the same result. But otherwise, this is not the case. Okay, so what's the relationship between map and fold? As it turns out, map is really just a special application of folding. More precisely, to get map or map prime, as it were, we can use fold right with the function that takes an argument and the initial value, or accumulator as we also call it, and then apply f to the initial value and cons it onto the accumulator, and the accumulator should then just be the empty list, because then we can map the elements one by one by starting off with the initial value being the empty list. So there's really no need to have map as long as we have fold right.